Okay, my name is David Canning. I'm from the Harvard Center for Population and Development Studies, and this is a lecture in the INTREC program on social policy and evaluation. So welcome to all our viewers today from the In-Depth Network and any other viewers that we have for this lecture. What I want to emphasize today is the importance of evaluation and causality. And essentially, we want causality for policy purposes. It's not enough just to show that there's an association between things. To show that one thing is linked to another is not enough for policy purposes. If we're going to do policy, we want to know if our policy works and is effective. And if we're going to design policy, we want to know that it's having a causal effect. And that's a really difficult problem. Most of the data that we have, most of the observational data, gives us associations. We can see that one thing is linked to another, but to say that it causes something is a much more difficult problem. It's a really difficult philosophical problem. There are actually different definitions of what we mean by causality, and none of them is entirely satisfactory. I'm going to sidestep that philosophical problem today and take a particular definition which is useful for implementation. It's a useful definition when we're actually doing the work. And the definition is a counterfactual one. And the idea of the counterfactual is we want to compare the outcome under treatment with the outcome when you don't have the treatment. So if we're interested in an effect of a social policy, for example, we might be interested in the effect of giving old age pension to people on their health. We might be interested in the effect of giving child grants. We might be interested in the effects of social networks on health. For any of those things, what we're going to say is the causal effect is the effect if you get the treatment, if you get the thing we're interested in, versus what would have happened if you didn't get it. So it's the difference between the outcome with the treatment and the difference outcome you would have got without the treatment. That in itself is a problem because we never observe both outcomes. If we give someone a treatment, we see the effect and the outcome with that treatment. And if we don't give someone a treatment, we see the effect of not giving them the treatment. But we never see the same person at the same time with and without the treatment. We can give a treatment to a person and see the effect, and then later on not give it to them and see what happens, but that's at different times. And it's not clear that the outcome will not have changed anyway over time. And so we have to have some sort of approach that will let us try to estimate the effect with and without treatment when we don't directly observe it. And so what I'm going to talk about are different ways of doing that. Just to give a concrete example, one of the key social determinants of health is income. So income and income inequality matter for health. And this is just a graph of 2005 data of life expectancy against income per capita at the national level across countries. You get the same result if you do it at the individual level. Richer people tend to have better health. And we can see that the relationship is nonlinear. So as countries get richer, they seem to get higher life expectancy. And at low levels of GDP per capita, under $10,000 a year, that effect is really, really big. And then there's a leveling off. Among rich countries, levels of life expectancy are quite similar, though there's a slight upward trend with income. And there are a few countries, outliers, that have low life expectancy, even at given the levels of income, and those tend to be countries with HIV/AIDS. This is the same graph drawn for the United States of income per capita against life expectancy at the county level. And what we can see is I've drawn the relationship in 1970 and 2005. And there's this relationship that higher income tends to go with better health. The interesting thing about this graph is that in 2005, the line is actually higher than before. And that higher line is probably because of advances in medical technology or other things that are affecting the relationship. If I just go back to the previous slide, we can also see this nonlinearity. In this slide was in levels of GDP, and that nonlinearity means if we redistribute income from the rich to the poor, average health tends to go up. And the reason is income really matters to the poor. Income has large effects on health for poor people, but not so large for rich people. And this gives us the idea that redistribution of income will actually be good for health. This graph is actually done with a log scale, which makes it look more linear. So we're looking at log income per capita on the bottom axis. So these graphs are highly suggestive of a strong relationship, but they don't imply causality. Something could be going wrong, which means that it's not really that income per capita is affecting health. And so the problem of making causal inferences and doing evaluations is that we have these problems that could be going on and making this not a causal relationship. And there are 4 problems that I want to talk about and that I'm going to go on and then suggest ways of solving. So if we look at the effect of income on health, it might be that it's not really that income is affecting health, but income is a proxy for something else. So that it's really some other factor like education or healthcare that affects health, and that those things are highly correlated with health. So rich people have high levels of education, they have better healthcare. So it's not really the income that matters, but the health of the healthcare. And that confounding is really this effect of an omitted variable bias. There's something else that's really driving the result, and that other thing is not being included in the model. If that's the case, we can have this strong association, but it doesn't imply causality. It means that if we were to raise someone's income, we might not see any effect on health, because it's not really that income that matters. It's just that we've left out the really important thing, which could be education. A second problem is reverse causality. The reverse causality problem is that it may not be that income is affecting health, it may be that health is affecting income. So there's not a lot of evidence that children who are well nourished and don't have infectious disease have better physical and cognitive development. And that better physical and cognitive development leads to better educational outcomes and leads to more earnings as an adult. And that means what may be going on in those graphs is not be that income is affecting health, but that health is affecting income. They're actually mistaking the direction of causality. If that's the case, then rising income may have no effect, because it's not income going to health. It may be that we really want to improve health so that we can get higher incomes. And so we have to think about reverse causality when we look at these relationships. Another problem is selection. There may be a selection bias. So that our sample that we're looking at may not be all the observations in the world. And they usually aren't. Even at the national level, a lot of countries are being left out of the analysis. And the countries that are left out of the analysis tend to be those with poor data. But having poor data is not random. These may be countries that are particularly low income and bad health. They may be countries, for example, affected by civil war, where the data collection is stopped. And it may be that those countries are different from the ones that we're observing. And so we're only observing the relationship in the selection of countries and the selection of individuals who happen to be on our sample. But that may not be everybody. And in fact, the effects may be going in the opposite direction in the people who are left out of your sample. So there's a worry about whether the sample is representative of the population. And finally, there's an issue of power, which is the sample big enough to detect effects? So a worry when we find that there's no effect is simply that the sample size is too small. So usually when we find an effect, we're pretty confident that we're seeing something. But when we find no effect, that could either be because the truth is no effect, or it could be that our sample is simply too small to see it, so that the sample is dwarfed by the noise, and we can't see what's happening in this small sample. So all of these problems mean that it's going to be very difficult to interpret observational data to make causal inferences and to evaluate policies and say that policies are having effects. And so what we want to do is come up with mechanisms that will address these problems. And I'm going to look at mechanisms for each of these problems. So the first set of approaches I'm going to talk about are statistical fixes for confounding. So this is the case whenever you have data, you have looked at a relationship, you see a relationship, but you're worried that you've left something out. So there's some other factor that's affecting the outcomes. I would say, sort of overall, looking at the big picture, we have solutions for most of these problems. What's very difficult is to solve all of them at the same time. So to solve all of them at the same time is hard. But if in a particular data set you understand that there's a particular problem with one of these issues, we often have a way of getting around it. So a thing that many people will be familiar with is the use of regression with controls. So in a regression analysis, you would run ordinary least squares or some other regression model, where you look at the output as a function of the treatment that you're interested in. And to correct for the omitted variable bias and the confounding, you will add more control variables. The problem with this is you never know when you've added enough controls. There may always be more omitted variables that have been left out of the model. A second approach is a matching approach, which is similar, but what it does is matches treated observations to control ones that are very similar and ideally identical. So the only difference between them is the treatment. And the third is a regression discontinuity approach. And I'll look at those in more detail. So this graph shows the relationship between years of schooling and the total fertility rate in sub-Saharan Africa. So on the bottom axis, we have the average years of schooling of women 15 years and older. And on the vertical axis, we have the total fertility rate, the births per woman. And what we see is this downward sloping relationship. That relationship is an association, but there are probably lots of other things going on in this data. There are two lines here representing two different time periods, 1980 and 2010. And so you could think of that as a time effect, that over time, fertility is coming down for women at the same level of schooling. However, it's not really a time effect. Time isn't having an effect on its own. What's really happening is other things are changing. Perhaps access to contraceptives, perhaps education of the women, perhaps social norms. All of these things may be changing and changing the relationship. And so this is really evidence that the relationship is misspecified. So if you estimated this relationship, you would immediately try to think, what is it that's changing over time that I've left out of my analysis that I want to put in? And so whenever we have time dummies or region dummies, they're really symptoms of omitted variable bias and confounding. There are things going on in the data that we don't understand that are showing up as these time dummies or region dummies or country dummies. But there are real forces at work there. But it's very, very common that we see this pattern that there are things going on which we're not modeling. And so to have a complete model, we'd want to add more variables to capture those, but we never know when to stop. A slightly different approach is the matching approach. I think this is actually superior to the regression analysis for several reasons. And the idea of the matching approach is to match each treated observation to a control observation with the same covariates. So what we're doing is finding for each person with a treatment, so for example, a person who has been to school and a control person who has not been to school, so one person has more years of education than the other. We want to see the effect of education. What we want to do is find a person who is identical in every way except for the education. So you want to find a person with the same socioeconomic background. He comes from the same neighborhood, has parents who have the same socioeconomic status, he has the same number of siblings, the house size is the same, the distance to school is the same. So everything about these people is the same, except one got the treatment and one didn't. And we can argue that the one who got the treatment was treated at random. So that the difference between these two people is exactly the counterfactual that we talked about at the beginning. The counterfactual is the person who didn't get the treatment is just like the person who did, except they don't have the treatment. This approach has a number of problems. One is that we can't get exact matches, so there are no two people who are exactly identical. And that lack of being identical, though, can be solved by getting approximate matches. And so if we get matches that are approximately the same, so two people are very similar, we're going to get good results. The worry, just like the regression analysis, is, however, that there is something that we've left out of the model. We have to match on everything. If there's something left out of the model that affects the outcome that we haven't matched on, it might be that thing. So matching also is the same problem about the covariates. If we are matching, there are different ways of doing the matching when we cannot get exact matches. A method that many people will be familiar with is propensity score matching, which is a system of matching based on the propensity of getting the treatment. I won't go into that in any detail. What I'm going to advocate, and what you'll see later on at what I'm going to ask people to do in homework 1, which is associated with the lecture, is quotient exact matching. And what quotient exact matching does is group the covariates into bins. And in these bins, the covariates are very similar. So for example, we might have everyone with education levels up to primary school, and then between primary school and high school, and then high school and beyond. So we have 3 bins of people with similar levels of education, and match people to people in the same bin. So if you're in the same bin as someone else, you're very similar, and that match, we think, is good enough to control for the fact that you two guys are very similar. You may not have exactly the same years of schooling, but you'll have a very similar level. An advantage of this approach is that it's very closely linked to the counterfactual. So the way we defined the causal effect was as the difference between what happens if you get a treatment and what happens if you don't. And what we're estimating here is the effect if you get a treatment versus the effect on someone else who doesn't, but that person is very similar to you. So the control is someone who is almost identical to you who didn't get the treatment. And that person serves as the counterfactual of what would have happened to you if you hadn't got the treatment. So the matching approach is a way of constructing the counterfactual. A third approach, which is actually more convincing than the other two, is regression discontinuity. The regression discontinuity approach works when there's a sharp divide in health inputs at some point in a continuous variable, the discontinuity. So what's happening is that there is a big change in the treatment at some point. And that change is within a variable that is otherwise continuous. And people on the other side of this discontinuity should be very similar and should have very similar outcomes apart from the treatment. And so what we do is only look at the effect of treatment in the region of the discontinuity. And what we can do is do a regression in the neighborhood of the discontinuity, or indeed just look at the difference between treatment and controls in the neighborhood of the discontinuity. This will actually become clearer if we look at some particular cases. So in this case, we see the effect of water treatment on health in the United States. And this is based on a paper by Cutler and Miller. And what they've done is, for lots of cities in the United States, they look at the health outcomes as a function of water treatment. And so this is a graph that they draw for Cincinnati. And they look at, for the Cincinnati water supply, when filtration was introduced and when chlorination was introduced. So filtration was introduced around 1906. Filtration was introduced around 1917. And then they look on the vertical axis at the typhoid fever mortality rate per 100,000 people. And what you see on the vertical axis is this mortality rate. And you see, prior to 1907, 1906, 1907, whenever the filtration came in, there was very high and variable fever death rates from typhoid. After about 1908, the death rates become very low and gradually decline. Chlorination is introduced in 1917. And we see very low levels of mortality from then on. So a regression approach would look at the filtration period versus the post period after the filtration. What regression discontinuity does is just look at the outcomes at the point where the policy is introduced. So in a standard regression analysis, you would look at the whole data set from 1900 to 1936 and analyze all the data. Regression discontinuity says there are lots of things changing over time. If you want to model the whole time period, you should really control for everything else that was affecting typhoid fever over this period. And we don't know what those things are. So what we do is we look at mortality just around the period of introduction of the policy. So if we look just around 1907, where filtration was introduced, in 1907 itself, we see very little effect, but by 1908, we see this big decline. So if we compare 1908, 1909 with 1905, 1906, we see a big effect. And the regression discontinuity effect is really the difference that's going on at the exact time of introduction. If we look at the same short interval of time for chlorination, we see very little effect. The outcome in 1919, 1920 is very similar to that in 1915, 1916 before the chlorination. So it looks like not much is happening when you introduce chlorination, but when you introduce filtration, we see very big effects. Maybe not immediately, but very shortly thereafter. And so what regression discontinuity argues is other things are changing, but the other things are not changing very fast. So we shouldn't expect to see big changes at exactly the time that we introduce the policy. So if we see big changes at exactly the time we introduce the policy, That's strong evidence that the policy works. And so what we do in that approach is actually throw away all the data that's not near the time of introduction of the policy. Because in order to include that data, we'd have to think about other things that were happening over time. And we essentially argue that without the introduction of the policy, we wouldn't have expected much to change over a very short interval. But that's not true over a long period of time. But over very short intervals, we don't expect much to change. If it was just one case, if we just had this one example of filtration and typhoid fever, you might think that it's by chance, that something else happened exactly in Cincinnati at this time. But what the authors do is they actually do this for every US city, and they have lots of graphs that are very, very similar. And then they do a regression where they pool all the information over all the cities, but in each case, only using the data from the few years around the introduction of the filtration, just looking what happened immediately after and immediately before. And that, I think, is quite convincing that the filtration actually worked. And it gets rid of this problem of unobserved variables of confounding. If it really wasn't the filtration, something else would have to be happening, something big, in all of these cities at exactly the time the filtration was coming in, and that seems highly unlikely. So this regression discontinuity approach is actually a very convincing way of looking at policy effects, and probably much more convincing than regression or matching techniques. This is an example from a recent paper I did with Alina Pradhan, and this was looking at the fertility and health effects of education. And the approach we use is actually very common in the literature now. It's using policy changes on education, particularly compulsory schooling laws. And what happened in Ethiopia in 1993 was an education reform. And that education reform removed school fees. It also changed the language of instruction from the national language to the local language. And what we saw is a big jump in education just at the time of the reform. And so what this graph shows is the average years of schooling of women in Ethiopia over time by year of birth. The red part of the chart are women who were not affected by the reform, they were too old. The blue part are women who were 7 years or younger at the time of the reform. So these are women who are girls who are just about to go to school or may not go to school, and the reform has happened before these girls are deciding to go to school. And for the women in the green area, they were born, but they were older than 7 when the reform happened. So they were still of school age. They're between 7 and 16. But they may not have gone to school. And essentially what we see is very little effect on these women. Basically, if they didn't go to school when they were 7, the policy reform didn't seem to affect them very much. But for women who were born from 1987 onwards, we see this big jump in education. The women who were born 1987 onwards get over 1 year of schooling extra because of the policy reform. So what's happening is the policy reform is leading to increased enrollment and increased educational outcome. Now, when we run a normal regression of health and education, we have all of the problems that we outlined for income. We have confounding, we have reverse causality. So it may not be the education, it may be something else. We know that children from parents who have higher socioeconomic status are more likely to go to school. So it may not be education that is causing good health, but it may be having high socioeconomic status parents. But here what we see is an exogenous jump in the education level independently of the socioeconomic status of the parents. And we can estimate the effect of that jump in education on outcomes. And that's a more convincing argument than a simple association, because what we're seeing here is a policy change leading to a change in education, and that change in education leading to changes in outcomes. And so we can associate the outcome change with an education change induced by the policy. And that makes us believe that the policy works, that the policy has an effect, because the timing of the education and health changes match the timing of the policy reform. So what we actually looked at here was the effect of the policy reform on reproductive health outcomes for these children. And basically what we're doing is comparing outcomes for girls just before the reform, who were slightly too old for the reform, with those who were just a little bit younger. And what we see are large and significant effects on teenage birth and teenage marriage. So that what's happening is the girls who are getting extra education seem to be delaying marriage. They're much less likely to get married before age 20, and they're much less likely to give birth before age 20. We'd also expect to see health outcomes, but these probably won't occur until later. There's quite a strong association between health and education at older ages. So highly educated people tend to have lower mortality at older ages. And this approach to using a policy variation in education and looking at the educational and health or fertility outcomes based on that policy, I think is quite convincing. So what we're doing here is using the effect of the policy to identify the effect of education. Whereas if we just looked at the education on its own, it's so correlated with other factors like socioeconomic status, it's very hard to work out what's happening. Of course, there's also the possibility that something else happened around 1993 that affected these women, and we can't rule that out. So there's an assumption that without this change, there wouldn't have been big changes in outcomes. But if other things are happening at the same time, we may not be getting the right estimate. Another way this has been used is looking at the effects of age eligibility for social grants in South Africa. So South Africa has old age pensions. It also has child support grants. And what this graph shows, it's based on a paper by Jacob Bohr, is the eligibility for child support grants by birth cohort and age. So on the vertical axis up and down, we have different birth cohorts running from 1991 to 1996. And on the horizontal axis, we have age of the child. Initially, the child support grant went up to children up to age 6. And so what we can see is that children up to age 6 got the grant. And if you're born later, you're at an advantage. The children who were born earlier didn't get the grant when they were young, because the grant wasn't introduced until they were almost 6. And so these older children get it just as they're approaching 6. And then when they're 7, they stop getting it. Later, the grant was then extended to age 13. And so what we see is when it's extended to age 13, children may have stopped getting it and then start getting it again, because they stopped getting it when they were 6. But now it starts again up to age 13, and so now they're eligible again. And in the diagram, a 1 means that they're eligible for a full 3-month period, and the fractions are proportions of a 3-month period that they're eligible for the grant. Later again, the grant was increased up to age 18 or 17. So up to when you're 17-year-old, you're eligible for the grant. And what we see then is this extension, which was actually introduced only for people born after a certain date, and so it doesn't have quite the same structure, but everyone born after January 1994 is eligible for this up until they're 17 years old. And so an interesting question is, what is the effect of this child support grant on health? So the child support grant will bring extra money into the household. As well as bringing in extra money, it's targeted at the children. So the money is in some sense labeled as belonging to the children. And so we would think that this money is spent on children and may change the household's behavior. So we'll get an effect just of having more money in the household, and we'll also get an effect of this labeling for children. And this money may then have health outcomes, that the health of these children may improve if this money is spent on things that affect health. One way of analyzing the data would be regression analysis, and basically looking at all of these children and looking at the people who get the grant versus those who don't get the grant. But then we have to think about other things that are going on. A more convincing approach is regression discontinuity. And this has been looked at in this, particularly for the effect of the grant on reproductive health and HIV. So if you look at the grant to teenagers between the ages of 14 and 17, children born in January 1993 are not eligible. Those born in January 1994 are eligible. We think not much else is happening over this very short time period. These children are just a year apart. And over this very short time period, we don't expect much to be going on, except that the ones born in January 94 are getting access to the grant. And so what we can do is just look at those children born in those adjacent cohorts and see what effect the grant has. And particularly for teenagers, the grant has an effect on staying in school. So because the household is getting some money and it's attached to the child is more likely to stay in school. And that increased staying in school may lead to a reduction in sexual behavior and a reduction in HIV incidence. So this is a way of testing whether there's an effect on income that is aimed at children, on educational outcomes, and then on health outcomes. And I think the more convincing approach here is a regression discontinuity, looking at adjacent birth cohorts who have different access to the grant, rather than running a regression over the whole grant. And again, it's closer to the counterfactual. The children born in January 1994 are very similar to those born in 1993, except the ones in 94 got the grant. So the treatment effect we see in the January 94 children, and the counterfactual, what we think would have happened, is what we observe in the January 1993.